This is a production of Cornell University.
Light's the ultimate source of energy on Earth. Through photosynthesis, it provides us with clothing, food, housing. For people that work with plants, it's absolutely essential for germination, phototropism, flowering, pollination. I see it as a first principle in the plant world. In fact, this is my high school textbook for biology. And it's light is the energy for life. And it goes on to a chapter telling us what is light at the time. Actually, I did stage lighting in high school. And my goal was to, for those that are older, to do light rock bands with Chipmunk, but it didn't happen. Although I did work on light and how it activates cells with Peter Hepler. And at the time, we looked at everything to understand it based on chemistry, physics, biology, history, and philosophy. And you'll see that approach here today. So, as Socrates said, follow everything to the end, wherever it leads you. And I ended up becoming a plant cell biologist and light microscopist. Wrote 2 books, both in their 3rd edition. And throughout these books, I try to help people understand, and actually that's really important, to understand light and cell biology based on chemistry, physics, history, and philosophy. So let's start from the very beginning. Oh, just came out last week. And God said, let there be light, and there was light. And God saw that the light was good. But let's get in a little more detail. Okay, so Christian Huygens figured light was a wave. It couldn't be a corpuscle, because if it was a corpuscle, then if this person was looking at the bird and this person was looking at the flower, the corpuscles would hit each other and just go everywhere. So light must be a wave. Well, Newton said, no, 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 light can't be a wave, because if you take a human here and you shine light on it, waves tend to go behind something. Next time you're walking by water and you see a stick coming up, you'll see the waves go around. But Newton couldn't see that, so he said light must be a corpuscle. Okay, this is what corpuscles look like. This is what waves look like. If it can't be a wave, and it can't be a corpuscle, maybe it can be a particle and a wave, or a corpuscle and a wave, or a particle or 2. And that's what I'll come back to. Thomas Young actually repeated Newton's experiment and found out that the light that hit both sides of the barrier actually went around. That Newton missed this. And actually, my students do this every year. Although it's really easy with a laser and very difficult with sunlight in England, because you don't get much brightness and coherence. But anyhow, this happened. So this was evidence that light behaved as a wave. Here's light hitting 2 different holes. They come out and they make a pattern like this. And Thomas Young said it made this pattern because when the crests came together, you get constructive interference. If the crests were out of phase, you'd get destructive interference, and that would account for the light and dark bands. You know, Thomas Young might have been kind of bright because he started off doing botany. Here's his first paper on opercularia. Okay, so light seemed to be a wave, and James Clerk Maxwell showed that it was an electromagnetic wave. So here's how he showed it. He took Faraday's experiment that when you move a magnet through a coil, you create an electric current in that coil. So see my thumb? That's the magnet. And my fingers are the current in the coil. That's what this symbol means. That you move a magnet up and down, and around it, you get a circle or the curl of the current. Ampere showed that if you have a current moving across an electric field, it will generate a magnetic field around it. This equation said, my hand is now the same as the equation. You have a current going this way, make a magnetic field that goes around it. Everybody clear on that? Okay, we'll get past the vector calculus now. Maxwell also assumed that the divergence of E equals 0. That means that there's no sources of electric fields or no sinks for electric fields. In other words, there's no electric field. Well, wait a minute. Isn't light the carrier of the electromagnetic force? We'll put that aside. And this here means that there's no magnetic monopoles. That means you can't have just a north magnet without a south magnet, or south without a north. And that part's actually true. Okay, Maxwell's math was a little too simple here, because this says as soon as you change the magnetic field, you get a change in the electric field. In other words, there's no cause and effect relationships. It happens simultaneously. Same thing here. You have a change in electric field, you instantaneously get a change in the magnetic field. And that shows up in his wave equation. Notice that the electric and the magnetic fields are in phase. Okay, so as long as we assume causality doesn't count, Maxwell's wave equation is good. Oh, let's also assume that conservation of energy doesn't count. Because here you have zero energy, maximum, 0, maximum, 0. Okay, there's a few flaws in Maxwell's equation, perhaps. We're going to question these assumptions. Einstein actually questioned the assumptions. He said, we should remember that the elementary quantum of electricity, epsilon, I call Q, is an outsider in Maxwell-Lorentz electrodynamics. The fundamental equation of optics will have to be replaced by an equation in which the universal constant epsilon, probably its square, also appears in a coefficient. I have not yet succeeded in finding a system of equations suitable for the construction of the elementary electrical quantum and the light quanta. The variety of possibilities does not seem so great for one to have to shrink from this task. And I didn't. And I'll tell you how I found the way. Okay, but let's start from the very beginning. Okay, in the beginning, there was energy. And one of the forms of energy, the 4 fundamental forces, one was the electromagnetic force, and it split and gave rise to matter and antimatter. Here's a symbol of a photon giving rise to a particle and an antiparticle. It's called pair production. Okay, there is antimatter in Ithaca. Bananas, which are full of potassium, mostly potassium-39, have a sizable amount of potassium-40, which is radioactive. And it decays into argon-40 by emitting a positron. So a positron is a particle of antimatter, and there's about one produced every 70 minutes. Also at Hugo Medical Center, there's PET scans, positron emission tomography, where you take fluorodeoxyglucose. This is really interesting. Otto Warburg found out that cancer cells ferment. They don't respire, they ferment. You would think it's the opposite. But because they ferment, they need tons of glucose. So you give the body fluorodeoxyglucose, and it goes right to those cancer cells. The fluorine gives off a positron. The positron meets with an electron from the cancer. It gives off gamma rays, and you have detectors that now can localize the cancer using positron emission tomography. And last week we heard that Margaret uses positron emission tomography to look at grafting. Okay, so there's 2 complementary processes, pair production, converting light energy into matter and antimatter, and annihilation, converting matter and antimatter into light energy, all based on E equals mc squared. Now, some of you must be thinking, if light can turn into antimatter and matter and antimatter can turn into light, could it just be that light is made out of matter and antimatter? Okay, let's look at what the big boys say about matter and antimatter. There's something called charge parity time symmetry, that if you want to convert a particle of matter to a particle of antimatter, what you do is you change the charge, you change the spin, the direction of spin, and you change the direction it moves in time. Okay? So if this is positive, 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 this is negative, 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 product of this is positive, product of this is negative, matter equals the minus of antimatter. Who here has seen time go backwards? I want to start with the assumptions of a scientist that what you see is pretty close to what's real. Not necessarily, but it's a great first approximation. Okay, so I've never seen like antimatter going backwards in time. I've never seen mitosis or meiosis, all those other cells that are made, come together and make one cell. Although 30, 40 years ago, I published a paper in the Journal of Irreproducible Results that said I did. Okay. And are elementary particles mathematical points, or do they have extension? I mean, what is actually the definition of matter? Definition of matter is something that has mass and extension. For example, compared to ideas. Robert Hooke wrote micrographia in 1665. Here's his microscope. And he said, I'm going to start this whole field of microscopy like a geometer would. I'm going to start with a point. So he looked at the point of a needle. And he saw how blunt it was. It had extension. He looked at a line next, like a razor blade, and saw how line-like it was. Okay, so this brings us now to about 1900. And Lord Kelvin, who actually came to Cornell and said it's the prettiest campus in the world, gave a talk which was entitled 19th Century Clouds Over the Dynamical Theory of Heat and Light. And in it he said, the beauty and clearness of the dynamical theory, which asserts heat and light to be modes of motion, which is waves, is at present obscured by two clouds. How could the Earth move through an elastic solid, such as essentially is luminiferous ether? Okay, so water waves move through water. Seismic waves move through rock. Sound waves move through air. What do light waves move through? They move through the luminous ether, luminiferous ether. But if you figure out the speed of light and the transverseness of the waves, that ether would have to be so viscous that would have stopped the Earth from moving. So it was a real conundrum. And remember how I told you that Maxwell didn't put any of the electrical properties into his light wave? He put them all into the ether. So the little balls are the electric current, and the big ones are magnetic forces moving around in circles. So here we had this ether that was thick enough to stop the Earth from moving that would carry the light waves. And then after Michelson and Morley did their experiment that said it doesn't matter which direction you move in the ether, the speed of light's the same, Einstein said, then there must be no ether. This must be people's imagination. And he banned the ether, it was gone. So now we have no ether, and now there's some room for the quantum mechanical photon. There was one other cloud over 19th century physics, and that was Maxwell-Boltzmann doctrine that said that pressure is caused by molecules, which are mathematical points, moving and hitting the edges of things. And the more you heat them up, the faster they move and the more pressure they exert. And certain and they would hold a certain amount of heat based on these motions. So you heat the molecules up and they move faster. So they're using that heat up and they're holding that heat. But there were some molecules that held even more heat than like helium, which is a monoatomic gas. Things like diatomic gases like hydrogen. So it turned out that hydrogen held, instead of 3/2 kT of heat, 5/2 kT, because they had rotational motion. So they can save that heat in rotating more. And actually, there's vibrational motion too in other molecules. For example, bromides 2, that has 7 kT of heat. So the more what's called degrees of freedom you have, the more types of motion you have. Translational motion, rotational motion, vibrational motion, you can hold more heat. So everything just didn't work like a mathematical point, and Lord Kelvin wanted to point that out. Now, I spelt that wrong. That's the right way. Wilhelm Wien wanted to apply Maxwell-Boltzmann movement of particles to understand black body radiation. He figured the molecules inside the black body were moving, and as they were moving, as you heated them up, they'd move faster and they'd give off higher energy light. And it seemed to work pretty well. For example, this black line is the actual data, and the red line is his theory. And of course, all of us as biologists, we jump at this and we go out for a beer and celebrate. I mean, this is really great. But physicists really do know how to measure things. And it wasn't good enough. So Planck looked at this and said, how can I improve this? Leibniz, one of the inventors of calculus, had the law of continuity. Nature doesn't do anything in jumps. Everything is continuous. If you read Origin of Species, Darwin will say, nature does nothing in jumps. Although he says it in Latin, I will screw it up. So you can look it up. So what Planck assumed that just maybe if these oscillators, these atoms in the wall, somehow discretely sent out light. Now, this was like a combination of the atom and the light, so it wasn't like a photon yet, but there was a discrete thing. Then he could model the black body radiation perfectly. And the discreteness related to the energy of that oscillator-light combination, which was equal to what Boltzmann called Planck's constant, times the frequency of the oscillation or light, or Planck's constant times the speed of light divided by the wavelength. Speed of light equals wavelength times velocity, frequency. Okay, but Einstein outplanked Planck. He said, I'm going to make light just a mathematical point as discrete as you can get. It seems to me that the observations regarding black body radiation, photoluminescence, production of cathode rays, on, everything you could see, can be understood better if one assumes the energy of light is discontinuously distributed in space. According to this assumption to be contemplated here, when a light ray is spreading from a point, the energy is not distributed continuously over ever-increasing spaces, but consists of a finite number of energy quanta that are localized in points in space, moved without dividing, and can be absorbed or generated only as a whole. Okay, how do you get a wavelength which is a length in a mathematical point. Okay, Robert Millikan tested Einstein's idea that if you shine light on a plate, electrons jump out, and you can measure the speed of those electrons or its kinetic energy by putting a negative charge here and preventing them from jumping off the plate. He did that, and he found out that as you increase the frequency of light, you increase the kinetic energy of the electrons, and the slope was exactly equal to Planck's constant, first measurement of Planck's constant. Okay. Then Johannes Stark said, well, if this light thing is a particle that's moving in one direction, it must have linear momentum. So we know the energy is hc over wavelength. In mechanics, linear momentum, energy is equal to the linear momentum times the velocity of that ball. So for light quantum, it would be equals PC. So for a light quantum, the linear momentum would be E over C, which is hc over wavelength c, which would be wavelength over, Planck's constant over wavelength. That's the linear momentum of a photon. The shorter the wavelength, the greater the momentum. You kind of know that. X-ray would knock you over, where a radio wave would just go through you. Actually, I want to do you a little calculation for you, because Einstein was really kind of screwy on his. Okay, so if classically P equals mv, and for a light quantum, P would equal mc, and since we know that E equals PC or P equals E over C, then P equals E over C and mc, just take this part, move the C over, and you get E equals mc squared. So actually, I just derived E equals mc squared only from the mechanical properties of light. And that's kind of happy. Uh-oh. But E equals mc squared is kind of like too big. Because in classical mechanics, the energy equals 1/2 mv squared. So for quantum, that would be 1/2 mc squared. So where'd the other half of the energy go? I'm going to answer that in a minute. One more thing. Richard Beth measured the angular momentum of light. Angular momentum classically is the mass times the angular frequency, angular velocity times the radius. He sent polarized light through a birefringent plate, and it rotated, and he measured the angular momentum of each quantum was h over 2 pi. Actually, independent of wavelength and frequency. It's the same for every single photon, wherever you are. That's the angular momentum. So this is the quantum mechanical photon. It has a speed, a wavelength, a frequency, an energy, a linear momentum, and an angular momentum. Although since it's a mathematical point, nothing's spinning. Just a number, all numbers. And I don't want you to forget interference that Thomas, I can't think of his name. Young, thank you. I'm getting too old. Knew, because as biologists, we know there's morpho butterflies or beetles that when the light hits and goes through a thin plate or separated points, you get these beautiful blue colors. And you get those beautiful blue colors as long as this distance is less than about a wavelength. So you can have photons that are about a wavelength apart, and you'll still get these beautiful colors. That'd be really difficult if light were a mathematical point. And just because this is a plant biology seminar, plants also use interference to make some of those beautiful blue colors. Okay, so Einstein sort of neglected interference. Planck, when he introduced Einstein for membership, nominated for membership in the Prussian Academy, said, sometimes, as for instance, in his hypothesis of light quanta, he may have gone overboard and the speculation should not be held against him. Niels Bohr in his Nobel address said, in spite of its heuristic value, however, the hypothesis of light quanta, which is quite irreconcilable with so-called interference phenomena, is not able to throw light on the nature of radiation. Robert Millikan said the conception of localized light quanta, out of which Einstein got his equation, must still be regarded as far from being established until it can account for the facts on interference and the other effects which seem thus far to be irreconcilable with it. We must withhold our full assent. And Hendrik Lorentz said the hypothesis of concentrated quanta is directly in contradiction with observed facts, namely that what is seen in the phenomena of interference. But then Arthur Compton did this great experiment. It was like a pool table. He took a photon and shot it into an electron, and the electron went back using up some energy, and the photon was scattered in this way with a little longer wavelength. If you use conservation of momentum, conservation of energy, and Einstein's special relativity, it all worked out. Compton got the Nobel Prize, and from then on, everybody believed the photon was a mathematical point. When I was working on my model, I talked to Kurt Gottfried, and he said, there's nothing here. It's done. Science has changed, though. Science used to be a way to understand the world. Now it's a way to predict what's going to happen. And that's a fundamental difference. That's why I'm a pirate. I think I can safely say, says Feynman, that nobody understands quantum mechanics. David Merman here at Cornell declared himself to be among those who feel uncomfortable when asked to articulate what we really think about quantum theory. Writing, if I were forced to sum up in one sentence what the Copenhagen interpretation says to me, it'd be shut up and calculate. Although just recently, Jim Baggett, and unfortunately died, Halbron, started to question this lack of free speech in science. Shut up and calculate how Einstein lost the battle to explain quantum reality. Actually, Einstein really questioned quantum mechanics. He even questioned his point-like photon. He wrote to Lorentz, I'm not at all of the opinion that one should think of light as being composed of mutually independent quanta localized in relatively small spaces. So I tell my students the most effective tool for your career in science is to have a rug and a broom. And if there's inconvenient facts, theories, or whatever, you just put them under there. John F. Kennedy wrote in Profiles in Courage, the first pressure to be mentioned is a form of pressure rarely recognized by the general public. Americans want to be liked, and senators are no exception. We prefer praise to abuse, popularity to contempt. We are anxious to get along with our fellow legislators, our fellow members of the club, to abide by clubhouse rules and patterns. The way to get along, I was told when I entered Congress, is to go along. But on the stairs up to our dean's office, it says to be defiant. Defy disciplinary boundaries, ask new questions, inspire pioneering solutions. Is it just aspirational, not something you should actually do? I have no sense of self-preservation. I got the Courage in Education Award for being fearless when it comes to anything. I want to tell you about my way of doing science. So I'm looking here in the unknown. I'm using my left brain and my right brain. Left brain's trying to take things apart and analyze them, get those facts. Right brain's trying to put them together to make a picture. But I also turn around and I look at the past to see if that structure is as good as people think it is. So for example, a tree may be shading all those lateral buds that aren't growing. But when the tree's chopped down, those lateral buds have a chance now to grow. And I'm just looking at those lateral buds. Kintsugi, and Brian will recognize Makoto Fujimura, is taking those old pieces that had just been laying around under the rug there and getting some very fine gold and putting them together and making something that's even better than the original. C.P. Snow said that no scientist or student of science need ever read an original work of the past. And just out of curiosity, anybody read that April 1953 paper by Watson and Crick? 1, 2, 3, 4, 5. Okay. I think it's bad advice and you should go read it. Okay, I'm a simple man. 1, 2, 3, infinity. After that, can't do enough controls, can't understand things, can't remember things. I'm just not smart enough for this kind of thing. So I try to find the fewest number of first principle ideas that I can put together. And I have to really question the assumptions to make sure they're true and coherent, non-contradictory. So I'm challenging two assumptions: that the elementary particle is not a mathematical point and that time goes forward and backwards. Ben Ginsburg came to my lab and it was looking at the Carnot cycle. Carnot cycle is a thermodynamic engine that you heat it up, the piston goes up, you cool it down, the piston comes down, and it converts thermal energy into work energy. There's no change in entropy. There's as much entropy formed as there is taken away in the cycle. So there's no relationship to the order of events in time and entropy. Yet you can only go clockwise in this cycle. You can't go counterclockwise to do it. So there's an order of events in time, even though there's no entropy. So when Ben's told me this, I said, this is great. I grabbed his arm, took him to the physical science library, which existed at the time, put in a VHS tape of Feynman talking about the reality of antiparticles. And what Feynman said was antiparticles are particles that go backwards in time. So if this machine were made out of antimatter, according to Feynman, it should just run in the opposite order. But since I believe that there's only one direction in time, and we published on this, I said there got to be a new symmetry. Instead of having positive and negative time, let's have positive and negative mass and figure out all the mechanics and how everything behaves. So I came up with a new symmetry. Instead of CPT symmetry, substituted time for mass. So it said that antimatter is the same as matter, but the charge, the direction of spin, and the mass, the sign of the mass, changes. Negative mass is something that exists in theoretical physics. This is Tommy Gold. Here's Bondi, who wrote this. Tommy Gold was at Cornell and also initially helped me with my work on the photon. So as botanists, we know that plants respond to gravity. We know something about gravity. If I'm dealing with negative mass, I wonder how it works with gravity. Here's Newton's universal law of gravitation. This is the causal force. This is the response force. The little mass moves in response to the gravitational force. Actually, if you put these two together, the little masses cancel out, which means the direction of acceleration depends only on the sign of the mass of the Earth. So if that's positive, both negative and positive mass will accelerate to the Earth. This will accelerate to the Earth because the attractive force, it goes the same direction. This accelerates towards the Earth because there's a repulsive force, but it goes the other way. So it goes towards the Earth. If we made up the situation of having a negative mass Earth, since that's negative, they'd both go away. Actually, if you have two masses that are exactly the same size, the positive mass would run away from the negative mass, and the negative mass would be attracted to the positive mass. So we'd have this thing actually chase each other. It'd look like this. And if you want, you could call it massless. But the trouble is, it would chase each other to infinity, faster than the speed of light. And that's a problem, because light only travels at the speed of light. I walked over to Ed Salpeter's office and told him about my idea. And it turned out he came to Cornell to actually work on, could the photon not be an elementary particle? And this paper by Fermi and Yang had just come out suggesting that mesons weren't elementary particles, but part matter and antimatter. Louis de Broglie had postulated this before, that the photon was made out of two semiphotons made out of matter and antimatter, but they were massless and electrically neutral. Okay, so plants have action potentials. Actually, the algal cells that I have down in my lab were the first cells that were shown to have action potentials. Monday, I'm giving a lecture in neurobiology on plant action potentials. So we know about plant electricity. Thales took amber. Anybody know the Greek word for amber? Electron. So he took amber, rubbed it with fur, and it attracted little pieces of straw. Complete botanical experiment. Okay, Latin word for amber, succinum. Succinic acid was first isolated from amber. Okay, and you can catch fossils in amber. Okay, Cavendish made a torsion balance. He put these huge, big lead balls and saw how they attracted each other and calculated the gravitational force. They said actually he weighed the Earth from that, which in fact he did. Coulomb created a much smaller version of this. Instead of 9-pound lead balls, he used little piths from the elderberry. So if you've done anatomy, you might have taken the pith plant that grows out there in the courtyard and used it to help you suction. Very light. And he found out that the force of attraction or repulsion depended on the charge and the distance between them, as well as a constant which has the electrical permittivity of the vacuum. Okay. Opposite charges attract, like charges repel. And if you divide the force by one of the charge, call it a test charge, you get the electric field around a charge. Electric field radiates out from a positive charge and in to a negative charge. Between two charges, you get a very strong field. If a charge moves, you make a magnetic field. The faster it moves, this is the velocity, the charge, the greater the magnetic field. Here's another constant, magnetic permeability, that gives you the quantitative difference. All right, so I have these two positive negative mass things that are moving together as a photon, but they're moving faster than the speed of light. So I have to slow them down to the speed of light. And actually the speed of light is equal to inverse of the electric permittivity and magnetic permeability. So there's some electrical magnetic components there that may be important. So if you have a positive charge move, or a charge moves, it generates a magnetic field. And that magnetic field actually generates an electromotive force in the opposite direction that slows this down. It's called self-induction, or the electrotonic state. And Maxwell said this is actually the fundamental quantity in the theory of electromagnetism. So we have these two charges, two masses, two charges. The positive charge moves away from the negative mass, but as it moves away, since it has a charge, it generates a magnetic field, which generates electromotive force in the other direction to slow it down. So now this catches up. So you actually get two particles in a wave. And that's what it looks like. And here's kind of a model. Okay, now I want to talk about the rotational motion. If E equals mc squared equals h nu, then we calculate the mass of a photon. And if we let the angular momentum equal mvr, the classical quantity, and set that equal to the quantum quantity, by doing this, we use Niels Bohr's correspondence principle. And since the angular velocity is equal to the angular frequency times r, we get this equation. And from that, we can solve for the radius of a photon. So the radius of a photon is wavelength divided by 2 pi. So that's how wide it is, or half wide. Okay? So we have these two things that are moving like this with angular momentum. So each photon, for example, an X-ray, would be tiny, kind of like a particle. And an infrared photon would be very wide. Since the radius is wavelength divided by 2 pi, the circumference is 2 pi r, is actually equal to the wavelength. And that is the fundamental wavelength in a photon. Okay. This looks messy, but it really isn't. This is the three-dimensional equation for the movement of these semiphotons. There's the radius, and cosine means it's moving in a certain way, or sine. So to have a cosine and a sine means it's moving in a circle. To have a cosine and a minus sign moving in a circle in the other way. So this just says the semiphotons are moving in a circle. And this is a vibrational frequency I had to just create them out of my own head to make sure they didn't crash into each other. Because if they crashed into each other, they turned into light. And I didn't want that to happen. So this is what it looks like. That's a photon. And it's difficult to see the 3 dimensions, so I divided it now into resolve what it looks like as it's coming to you or looking from the top. Everybody see the particles in the wave? Same time. Do it again. Okay. Schrodinger wasn't able to come up with an equation for the photon. He could come up with one for electrons, which is spin 1/2. And in his equation, this n equals 1. I made this n equal 2 for a photon. This is the kinetic energy. This is the potential energy. This is the total energy. And I'm just going to say, if you solve this, you can solve this equation if you make a wave function that describes your photon. So here's my wave function. In essence, cosine plus I sine. That's the circle. And it takes a certain amount of time to go around the circle. All right, there's the wave function as constant. Now it has this I in there, imaginary number. So with the imaginary number, people don't use real space. People, I mean physicists, don't use real space. They use what's called phase space or configuration space or imaginary time. Okay. But I look at this as a transverse plane where there's actually rotational motion going. Caspar Wessel in 1799 was a map maker. And he figured out that he could use imaginary numbers to make ordered pairs. With the x-axis gives you the longitude, or the real axis gives you the longitude, and the imaginary axis gives you the latitude. Just keep two numbers that you can't add together. It keeps them separate. It's easy for the bookkeeping. So the energy of the binary photon that was twice as big as just the translational energy, you add the rotational energy and you get the full energy. Okay, now I just want to add Coulomb's law to the wave equation. So this, and this is the wave equation. This and this is Coulomb's law. We do it in the x, y, and z plane for the two photons. That gives us the electric field on each one. And I can sum them together to see what the electric field caused by both are. Also, I could do the same thing for the magnetic field. And here you want to use the velocity instead of the position. But you get the velocity. Note, I'll just show you in a second. Put them together, and you get the magnetic field. So imagine this is positively charged, and the blue one's negatively charged. Here, if they fly over this electron here, they're going to add no electric field. They cancel each other out. As they widen and separate, they'll put a little bit of electric field on here, a lot, none, and then an opposite directed field. So it actually have a sine wave, an electric sine wave going over that electron. And here's what it looks like in vector form. The pink wave will be the sinusoidal electric field, and the green will be the circular magnetic field. They'll be a quarter of a wavelength out of phase and orthogonal. Going to hit an electron, boom, send it up into another orbit. Einstein wondered what would happen if he traveled at the speed of light. For Maxwell's equations, everything stops. So Einstein concluded time must stop. But for here, it actually keeps going because the two things are self-regenerating because they're out of phase. So this is what it looks like. Sinusoidal electric field pulls an electron up to the next orbital. This is for hydrogen. Here's a hydrogen atom. There's the electron. Photons coming up. Absorption, very much like photosynthesis. Just a quick thing. There's a Kirchhoff diffraction equation describes how things look in a microscope. It works for everything. The trouble is, it's not consistent with Maxwell's equations. Okay, if you have a spherical particle, in a microscope, it doesn't look like, confocal microscope doesn't look like a sphere. It looks like this proloid form. And Kirchhoff's diffraction equation describes this perfectly, but it's not consistent with Maxwell's equations because Maxwell's equations has two waves that are in phase, and that's not allowed with the assumptions of the Kirchhoff diffraction equation. So Poincaré, Sommerfeld, Hans Bethe all said Maxwell's equations don't work. Okay, but everybody lets it go. But the binary photon has the two fields out of phase. Here's a picture of the binary photon in plane form in Maxwell's equations. You still have an electric field, still have a magnetic field, have an electric field, magnetic field, always, but with Maxwell's equations, they disappear. And that's why they won't describe diffraction. Okay. The point spread function is what we use to tell the relationship between our image and reality. These are the typical equations that are used, and actually you can't find a derivation for them anywhere. Zeiss published them once, that was enough, but there's no derivation. As a matter of fact, they use different functions to get the axial resolution and the lateral resolution. Using the binary photon, I can use just one function and just say that the axial is about 3 times greater than the lateral resolution because the photon travels about 3 times more distance than it is wide. So taking the geometric properties of the photon. Okay, in one cycle, the photon goes like this. And this is pi times greater than that. Polarized light is completely understandable when you have a sine wave like this. Photons have no dimensions, no sidedness. Can't understand polarized light. That's DNA. Here's a fiber cable from Teifer. Just one last thing. Einstein predicted that starlight would go by the sun and have what's called a double deflection. So you turn the telescope up higher and you see the star here, even though it's really. And he said it has a double deflection because the mass of the sun warps both space and time. But think for a second. If the photon from the star had 0 translational energy, it would just fall into the sun. If it had infinite translational energy, it wouldn't be bent. The fact that it's bent twice as much as just a Newtonian corpuscle would be bent means it has the translational energy is only half the energy. The other half is the rotational energy. So you don't have to say time, space is together and warped and all that stuff. You can just say that the photon has a few more properties than Einstein gave it as a mathematical point. Lorentz wished that physics would go back so he can imagine things in space and time. The young guy said, no, no, no. I think modern physics has definitely decided in favor of Plato. In fact, the smallest units of matter are not physical objects in the ordinary sense. They are forms, ideas, which can be expressed unambiguously, only in mathematical language. Those ideas have no extension. But I think a photon is a physical object. It has extension and could be pictured in ordinary space and time. So I think on the surface, quantum mechanics and relativity may seem to be profound. But deep down, I think they're superficial. Okay, that's it. I'm over, so. Any questions? Tom.
Andy showed sweeping things under the rug as opposed to using that as material for a testable hypothesis.
Oh, yeah.
Why not? Can you not derive testable hypotheses from whatever you want to call the trash you were sweeping under the rug?
Yeah. So let me give you my own. So first of all, if you're in a shut up and calculate environment, there's no testable hypotheses. All right. But I'll give you one of my things. So I have these masses at the end of like a string. I don't know the shape of those masses. Say they're more than a mathematical point, then the positive charge, say, could push apart the other possible charge, and they'd split. Poincaré say you need a Poincaré force in order to pull them in. And then, so if you have that other force, then what's the shape of the electric field? Is it exponential instead of linear, as I showed it? That's called the Yukawa force. There are actually, if you have an open mind, sweeping under the rug could just be collecting facts that need to be tested.
I read about half the paper right here. In the early part of the paper today, you mentioned that the matter antimatter creates possibility of the one chasing the other,
right.
So translational motion. How in your model does the rotational momentum and rotational motion come into play? Okay, the paper discussed
right.
translational motion, but how do we get that rotation?
Oh, how do we get the rotation?
Yeah.
Oh, so angular momentum is conserved.
Yeah.
So once it's emitted with one wavelength and therefore angular momentum. So I can just say it as an atom, a Bohr atom. Each electron stays in its orbit because angular momentum.
Yes.
Oh, yeah.
And in this case, we have the two particles, but there's no.
What's the charge between the those fields that I showed you actually take into consideration the three-dimensional charges that are there, but it doesn't really answer your question.
Yeah.
It's a sort of a description of the charges that are there, but not an explanation. Yeah, that's right. That's right.
Rotation.
That's right. I need to do that, or we can do that.
How do you prevent them from hitting each other?
So that longitudinal motion actually prevents them from ever touching each other. Yeah.
Okay.
Yeah. But I created that just on a whole cloth in order to make sure they don't touch each other. But actually, it worked out kind of nicely. The entropy of a photon is 3.6 K. So the entropy of a single particle is 1/2 K. And so you add degrees of freedom and you get more. So 3.6 K is like basically 7/2 K. So you look for 7 types of motion. And so there should be about 7 types of motion, but I just sort of made up that vibrational thing. I originally had a much simpler formula, but the photons wouldn't interfere constructively and destructively the way you observe. So I had to add like a square, 2 pi square term, and got it cosine squared instead of just cosine.
Really interesting talk. I was wondering, so the Super Kamiokande reactor in Japan, showed evidence for free neutrinos that are free from electrons and different flavors producing different halo effects. And these neutrinos are undetectable by our sensors, except when they interact with another particle, when they hit an electron and produce light. So how does your model account for the production of light by a particle that moves faster than the speed of light? Because if we assume that light has a set limit of its speed, then this particle couldn't be carrying light
Oh,
faster
okay.
than that.
So the center of gravity of the photon actually moves at the speed of light. But since it's vibrating like this, it has to move faster and slower on both sides. The average is always actually the speed of light. So the photon itself moves at the speed of light. One thing about neutrinos, Max Born initially and then de Broglie thought that once neutrinos were discovered, that the two particles would be neutrinos. And since neutrinos may or may not have a magnetic moment, it's not certain, and may or may not have a mass, it's not certain. I mean, this is even more certain, I think, than the neutrinos. These particles I'm talking about may be similar to neutrinos, neutrino and antineutrino.
So how would the interaction of a neutrino with an electron produce these photons in that case? Is it
Oh, I can only answer very vaguely, and is that if you have an interaction that's going to cause that lead to a certain energy production, if that energy production could give off a photon of whatever the particular wavelength should be. But I can't really answer that question.
This has been a production of Cornell University, on the web at cornell.edu.